I'm going to wrap up keyword spotting by talking about yet another interesting paradigm for a real-world deployment. We talked previously about streaming audio and how that's actually important. Now, I'm going to talk about how to efficiently deploy keyword spotting in a production situation. Remember that a lot of our problems really stem from the fact that TinyML is extremely resource constrained, though it can do this with extreme efficiency from a power perspective. Well, there's a trade-off we make, and therefore we end up with these very, very small models that we train, and they're efficient in terms of the number of parameters we have, but we end up by making many trade-offs, compromises, right? Think for a second about the kind of trade-offs we end up making. What happens to the number of words that you can actually get the keyword spotting model to recognize? It's a very small network, so you really can't get it to remember too much. The other thing is that we have only a handful of keywords, and getting accuracy, could be really difficult because the network is really simple. Ultimately, the two things add up to a limited user experience or quality of experience for the end user because the model is extremely simple. Of course, you can make enhancements to create increase the model slightly and so on and forth, but you get the general idea that no matter what you do, you've got a strong confinement in which you have to live in. Well, now let's take a look at the big picture, right? When we start off, we have the right microcontroller. From the microcontroller, which is running the neural network, we can do a little bit of processing there. But if we need more capabilities, we need to somehow be able to move the data up to the cloud where there are more computational resources that can run much larger neural networks. In that way, we can effectively do some initial processing on the local device and then do more on the remote device. So if you remember the animation I keep showing you, which is Alexa, and then says, hi, Rahul, and then I say, dim the lights. Understanding the dim the lights it requires a bit more processing. So that's typically offloaded to the cloud. That's one way we have effectively increased the size of the processing capabilities of the network in terms of the overall vocabulary. So you've got to think about keyword spotting in the context of the bigger picture, not just the keyword and the processing locally. So now instead of always going to the cloud, which can cost a lot of energy, are there other ways to mitigate this, right? Are there only these two extreme endpoints? No, right? Because you go from TinyML microcontrollers, you might have a phone or you might have a smartwatch, which might have a really good processor. And then you might be able to actually offload to your PC or then something else and then send it to the cloud. So there's a lot of this computational hierarchy that you have. And the question is, how do you leverage that? And that's where the cascading comes in. The cascading is this idea that you have a little model to do something and then a bigger model to do something else in order to unlock the overall capabilities that you can actually want from an application. So now, instead of going to the cloud, one of the things that we can obviously do is change that step in the middle. We can use a secondary larger model on a larger local device like your phone. So run a very small model on your microcontroller, and if it detects something that you think is interesting, and maybe it's not very confident, you can also run it in the nearby phone, smartphone element. That communication energy between the microcontroller and your phone is going to be much less than the communication energy that is needed between your microcontroller trying to talk to a cloud server, just from a pure infrastructure standpoint. So you can intelligently try and do a system architecture to get the TinyML application to be a bit more powerful than you want. Let's take a real world example, for instance, of how this can actually be done on a smartphone. A smartphone has a lot of capabilities, but it also has TinyML in it. Think about the fact that, for instance, when you say, hey, Siri, it's something that your phone is constantly able to recognize throughout the day. As long as it's got a battery, it's able to respond to, hey, Siri. But how do you think they are able to do that? By having you continuously listen for an audio stream? Turning the mic on and doing signal processing actually costs a fair bit of energy that will drain your battery very fast. So can you architect the system to be efficient is the key question here. So in the example that we kind of just looked at, hey, Siri comes in, and then you've got some mechanism, the detector, that wakes the phone up, that allows you to get more capability that's up in the cloud. So for instance, you say, hey, Siri, play my favorite song. Well, okay, that's pretty complicated. So that requires, hey Siri, to activate your phone. The phone has to recognize that there's something else you have said, which is play my favorite songs, which means that you've got to figure out what your favorite songs are in the cloud and then start playing things. So there's a fairly complicated pipeline here. So how can we enable this to be continuous, right? Always on machine learning. Well, that's where the cascading aspect really comes in. What you want to do is that you have to have a TinyML subsystem or an always on processor module that's physically on the chip, a computing subsystem that is separate from your main application processor that is constantly listening to this audio that is coming in and then using a TinyML model that is continuously running. And then if it detects something interesting, then it wakes up the bigger processing engine. And that bigger processing engine, which is much, much more accurate, can then figure out, for instance, with much greater confidence, if it should really be invoking the cloud, which is very energy inefficient if you get it wrong. And of course, you don't want to have false accepts. So this is the fundamental idea behind cascading architectures is in fact that if it is exactly how Hey Siri works, and in fact is also almost like how OK Google really works on your smartphone devices. TinyML is part of virtually every single phone that's out there. So taking a step back, the TinyML aspects, right, the always on processor is the kind of stuff that's running exactly like on the microcontroller that we'll be using, which is a Nordic processor. While your board is about the length of my finger, the actual chip or the microcontroller itself is really, really small. And that actual microprocessor is found on many phones. Now, by comparison, the bigger network, which has much more capability and is much more accurate, is actually running on a full Apple processor, which can consume anywhere from 1 to 3 watts. That's a lot of energy compared to the 10 to 20 milliwatts of energy that a TinyML device typically consumes. And that's the critical thing. The cascading architecture is a coupling of different models working together on different physical subsystems. And that's the key takeaway here. And the reason we end up doing cascade architectures is because they give us 2 ROC curves, right? And so on the x-axis, we have the false accepts. On the y-axis, we have the false reject rates. But by having 2 models, we can effectively have 2 operating points simultaneously that you can move around. And that gives you much more flexibility in the space. When we get into part 3 of this course, we'll go much deeper into cascade architectures as well as the streaming audio. With that said, the next time you say, hey Siri, I want you to think about all the brilliant mechanics from the machine learning to the embedded systems, to the streaming audio, to the cascading, all this stuff that's actually happening behind the scenes. It's beautifully executed. And that's really what gets me excited about TinyML. Again, remember, this is just the tip of the iceberg. And there's much more exciting stuff that's coming down. So stay tuned for that.